Welcome to Science Aura. I am Dr. Sachi Vale. Beneath the restless surface of our oceans lies a silent, invisible world. For decades, this dark abyss has served as the ultimate sanctuary for the most devastating weapons ever created by humanity. But a revolutionary breakthrough in quantum physics is about to strip away this veil of secrecy, changing the modern world forever. The apex predator of the deep has long been the stealth nuclear submarine. These massive leviathans of steel glide silently through the crushing depths, carrying arsenals capable of ending entire civilizations in a matter of minutes. They are the ultimate instrument of geopolitical power, operating unseen and unheard beneath the waves, casting a long shadow over global security. These submarines form the most resilient and crucial leg of the nuclear triad. This strategic framework relies on land-based silos, strategic bombers, and submarine-launched ballistic missiles. While silos and bombers can be targeted in a sudden preemptive strike, submarines hidden deep within the ocean guarantee a devastating retaliatory blow against any sudden aggressor. The immense volume of the world's oceans provides hundreds of millions of cubic kilometers of hiding space. The physical properties of dense seawater effectively block electromagnetic waves, rendering traditional radar systems completely useless beneath the surface. This unique environment has allowed submarines to operate with near impunity, shrouded in complete, absolute darkness. This absolute invisibility creates the very foundation of mutually assured destruction, a terrifying but effective balance of global power. As long as a nation's submarines remain undetected and capable of firing back, no adversary would dare launch a catastrophic first strike. The survival of humanity has ironically depended on these unseen vessels lurking in the dark abyss. For over half a century, military engineers have engaged in a relentless game of cat and mouse. The primary tool for hunting these hidden giants has always been sonar, utilizing sound waves to navigate, communicate, and detect objects underwater. Active sonar emits loud acoustic pulses, pinging the surrounding environment and listening for the telltale echoes of a steel hull. However, active sonar reveals the hunter's position as well, turning the search into a dangerous gamble. Therefore, submarines heavily rely on passive sonar, quietly listening to the ocean's ambient noise to detect the faint mechanical hum of enemy propellers or internal machinery. The ocean becomes an invisible acoustic battlefield where absolute silence is the ultimate weapon. In response, submarine design has evolved into an obsessive pursuit of acoustic stealth. Modern hulls are meticulously coated with thick layers of specialized anechoic tiles. These rubberized, sound-absorbing materials are engineered to trap and dissipate incoming sonar pings, drastically reducing the acoustic signature that bounces back to the searching enemy naval vessels. Furthermore, the noisy cavitating propellers of the past have been largely replaced by advanced pump jet propulsors. Inside the submarine, heavy machinery and nuclear reactors are mounted on sophisticated isolation cradles, dampening internal vibrations before they can radiate into the surrounding water. They have essentially become silent acoustic ghosts in the deep sea. The ocean itself aids in this concealment. Variations in temperature, salinity, and pressure create complex thermal layers known as thermoclines. These layers act like acoustic mirrors, bending and refracting sound waves, creating massive shadow zones where a submarine can hide completely undetected by surface sonars. The acoustic arms race has reached a frustrating plateau. As acoustic stealth technology approaches physical perfection, traditional sonar is becoming increasingly obsolete. Submarines are now so quiet that their acoustic emissions often blend seamlessly with the natural background noise of the ocean, from snapping shrimp to shifting tectonic plates. Finding a modern stealth submarine is like finding a specific whisper in a hurricane. This growing acoustic blindness has sent shockwaves through naval commands worldwide. Billions of dollars have been invested in advanced signal processing algorithms and massive sonar arrays, yet the detection ranges continue to shrink. The strategic advantage is heavily tilting in favor of the hiding submarine, creating a dangerous imbalance in the global security dynamic. Military strategists realized that relying solely on sound was a losing battle. They needed a new medium of detection, one that could not be absorbed by rubber tiles or deflected by thermal layers. They needed to look beyond classical mechanics and delve into the fundamental fabric of reality itself. The solution lay hidden in the microscopic world of subatomic particles. The rules of this deadly game are being rewritten not by naval engineers, but by quantum physicists. A profound paradigm shift is emerging from high-tech laboratories, leveraging the bizarre and counterintuitive laws of quantum mechanics. We are entering an era where the fundamental building blocks of the universe are being weaponized for unparalleled sensory supremacy. Welcome to the strange and fascinating world of quantum technology. At the subatomic level, particles behave in ways that defy classical physics. They can exist in multiple states simultaneously, a phenomenon known as superposition, and become inextricably linked across vast distances through quantum entanglement. These are no longer just abstract theoretical curiosities. Scientists are now harnessing these delicate quantum states to create measuring instruments of unimaginable precision. By isolating and observing individual atoms or electrons, researchers can detect the most minute environmental changes. This transition from theoretical physics to practical engineering marks the dawn of the second quantum revolution in human history. The most disruptive of these new technologies, particularly for the future of naval warfare, is the quantum magnetometer. Traditional magnetic sensors have existed for decades, but quantum variants operate on an entirely different level of sensitivity. They do not just measure the strength of a magnetic field, they measure its fundamental interaction with quantum states. At the forefront of this revolution is a device with a rather unusual acronym: SQUID. SQUID stands for Superconducting Quantum Interference Device. It represents a monumental leap in our ability to detect magnetic anomalies. To comprehend the power of a SQUID, we must first understand the remarkable physics that govern its operation at temperatures near absolute zero. The core principle behind SQUID technology is superconductivity. When certain specialized materials are cooled to extreme cryogenic temperatures, they undergo a phase transition. They suddenly lose all electrical resistance, allowing electrical current to flow continuously without any energy loss. This creates an environment where quantum effects can be observed macroscopically. In this superconducting state, electrons pair up into what are known as Cooper pairs. These pairs condense into a single macroscopic quantum state, moving in perfect synchronization. They flow through the material like a frictionless fluid, governed by a single, unified, quantum wave function. This delicate state is the highly sensitive canvas upon which magnetic fields interact. A SQUID consists of a microscopic superconducting loop that is deliberately interrupted by one or two incredibly thin insulating barriers. These barriers are called Josephson junctions. According to classical physics, the electrons should not be able to pass through this insulation. The circuit should be broken, and the flow of electrical current should completely stop. But in the quantum realm, particles do not always obey classical barriers. Thanks to a phenomenon called quantum tunneling, the Cooper pairs of electrons can literally instantly pass through the insulating gap. They tunnel through the barrier without ever existing in the space between, maintaining their delicate superconducting current across the interrupted loop structure. This quantum tunneling creates an electrical circuit that is exquisitely sensitive to the tiniest fluctuations in external magnetic field. When a magnetic field interacts with the superconducting loop, it alters the phase of the quantum wave function of the tunneling electrons. This minute phase shift translates directly into a highly measurable change in electrical voltage. The sensitivity of a SQUID system is truly staggering. It can detect magnetic fields that are billions of times weaker than the pull of a standard refrigerator magnet. To put this into perspective, a SQUID is sensitive enough to measure the incredibly faint magnetic fields generated by the electrical firing of individual neurons inside a human brain from outside the skull. Because SQUIDs are so sensitive, they must be heavily shielded from background electromagnetic noise when used in medical or laboratory settings. They are often housed in massive, magnetically shielded rooms. But military scientists realize that this extreme sensitivity could be weaponized. Instead of shielding the SQUID, they decided to expose it to the open environment. Operating a SQUID outside the laboratory presents immense engineering challenges. The device must be kept at cryogenic temperatures, typically requiring complex cooling systems, utilizing liquid helium. Maintaining this extreme cold in a rugged military environment, such as aboard an aircraft or a turbulent naval vessel, requires groundbreaking advancements in cryogenics. Recent developments in high-temperature superconductors have begun to mitigate this issue. These new materials can achieve superconductivity at relatively higher temperatures, allowing them to be cooled by liquid nitrogen instead of the much more expensive and difficult-to-handle liquid helium. This single advancement has made field-deployable SQUIDs a practical reality. Now, let us apply this mind-bending quantum technology to the vast expanse of the world's oceans. The Earth itself acts as a giant dynamo, generating a constant and relatively predictable magnetic field that envelops the entire planet. This natural magnetic grid penetrates deep into the oceans, interacting with everything it encounters beneath the restless surface waves. A modern nuclear submarine is essentially a colossal cylinder constructed from thousands of tons of high-yield steel. Because steel is a highly ferromagnetic material, it inevitably distorts the Earth's local magnetic field lines. The massive hull concentrates the magnetic flux, creating a distinct and measurable disruption in the planet's otherwise uniform magnetic grid. As the submarine silently moves through the water, it drags this localized magnetic distortion along with it. It creates a moving anomaly, a magnetic footprint that travels across the ocean floor. While acoustic stealth technologies can effectively silence the mechanical noise of the submarine, they are completely powerless to hide this massive magnetic disturbance effect. Military forces have long understood this vulnerability. They have used traditional magnetic anomaly detectors, or MAD systems, for decades. These classical sensors are typically mounted on the extended tail booms of maritime patrol aircraft, keeping them away from the magnetic interference of the plane itself. They fly low over the ocean, hunting for hidden submarines. However, these traditional MAD sensors have severe physical limitations. Their sensitivity is relatively low, and magnetic field strength decays rapidly with distance. This means the aircraft must fly dangerously close to the water's surface and directly over the suspected submarine to get a reliable reading. It is a slow, inefficient, and highly localized search method. This is where SQUID technology completely revolutionizes the battlefield. Because a SQUID is exponentially more sensitive than a traditional magnetometer, it can detect the magnetic anomaly of a submarine from significantly greater distances. We are no longer talking about detection ranges of a few hundred meters, but potentially tens or even hundreds of kilometers away. The introduction of SQUID sensors expands the search volume by orders of magnitude. A single aircraft equipped with a quantum magnetometer array could scan massive swaths of the ocean in a fraction of the time it would take a traditional MAD system. The submarine's magnetic footprint, once a faint whisper, becomes a blindingly bright beacon to these quantum sensors. But extreme sensitivity brings its own set of complex challenges. A SQUID will detect not only the submarine, but also every other magnetic fluctuation in the environment. Solar flares, ionospheric storms, ocean currents, moving conductive salt water, and even geological formations on the seabed all create magnetic noise that can obscure the submarine's delicate signal. To solve this, scientists do not use just one SQUID, but arrays of multiple SQUIDs arranged in specific geometric patterns. These arrays function as magnetic gradiometers. By measuring the difference in the magnetic field between slightly separated sensors, they can effectively cancel out the large-scale background noise while amplifying the localized submarine anomaly. This hardware solution is coupled with incredibly advanced signal processing algorithms. Artificial intelligence and machine learning models are trained on vast datasets of oceanic magnetic noise. These sophisticated algorithms can filter out the chaotic background interference in real time, isolating the specific, unmistakable magnetic signature of a stealth submarine. The implications are absolutely terrifying for submarine commanders. For decades, they have relied on the thick, opaque layer of the ocean to hide their massive vessels. They have mastered the art of hiding in thermal layers and creeping silently at ultra-low speeds. But against a network of quantum magnetic sensors, these acoustic tactics are entirely rendered useless. You cannot hide magnetism with rubber tiles. You cannot deflect magnetic fields with water temperature variations. The fundamental physical presence of thousands of tons of steel inherently betrays the submarine's location. The ocean, once an impenetrable shield of darkness, is rapidly becoming completely transparent to the unblinking eye of quantum sensing technology. This concept of the transparent ocean represents the most significant shift in naval warfare since the invention of the submarine itself. It threatens to completely upend the strategic balance of power that has maintained global stability since the end of the Second World War. The ultimate hiding place is being illuminated by the precise glow of quantum mechanics science. The deployment strategies for these quantum sensors are evolving rapidly. Initially, SQUID arrays will likely be integrated into the next generation of maritime patrol aircraft and anti-submarine helicopters. These airborne platforms can rapidly respond to suspected submarine contacts, sweeping vast areas of the ocean with an unprecedented level of magnetic precision. But aircraft are only the first step. The true realization of the transparent ocean will come from massive, distributed networks of autonomous sensors. Imagine fleets of high altitude, long endurance, unmanned aerial vehicles continuously loitering over critical strategic choke points. They would cast a permanent quantum net monitoring all underwater traffic in real time. Beneath the surface, the ocean will be seeded with autonomous underwater gliders and smart buoys equipped with miniaturized SQUID sensors. These silent drones can drift for months, creating a vast, interconnected web of magnetic surveillance. They would communicate via acoustic modems, relaying detection data back to surface command centers with devastating accuracy. The ultimate high ground for quantum surveillance is low Earth orbit. While detecting a submarine's magnetic anomaly from space presents immense technical hurdles due to the distance and the ionosphere's interference, research is actively underway. Satellite-based quantum magnetometers could eventually provide continuous global coverage of all submarine movements. If a nation achieves satellite-based quantum tracking, they would possess a godlike view of the maritime battlespace. No submarine could leave its home port without being instantly detected and continuously tracked throughout its entire patrol. The strategic element of surprise, the very core of submarine warfare doctrine, would be completely and permanently eliminated. A submarine's primary, and arguably only, defense is its invisibility. Unlike surface ships, submarines are relatively slow and incredibly fragile. A single torpedo hit is almost always fatal. If a submarine is detected, it is immediately vulnerable to attack from aircraft, surface ships, and enemy-attack submarines. Stealth is not just an advantage, it is survival. Without the cloak of invisibility, a multi-billion-dollar nuclear ballistic missile submarine transforms from a strategic deterrent into a massive, slow-moving vulnerability. The crew inside, once confident in their ultimate secrecy, would find themselves constantly in the crosshairs of enemy tracking systems, aware that their exact coordinates are known to the adversary. This sudden vulnerability fundamentally disrupts the global nuclear deterrence strategy. The nuclear triad relies on the absolute guarantee that submarines will survive a first strike to launch a retaliatory attack. If an adversary believes they can simultaneously track and destroy all enemy submarines, the terrifying calculus of mutually assured destruction is broken. This creates a highly destabilizing geopolitical environment. In a crisis, a nation might be tempted to launch a preemptive first strike against an adversary's submarine fleet if they know exactly where they are. Conversely, a nation, knowing its submarines are being tracked, might feel pressured to launch their missiles early before they are destroyed preemptively. The paradox of increased visibility leading to increased global instability is a major concern for military strategists. The transparent ocean does not bring peace. It brings a hair-trigger environment where the margin for error is reduced to zero. Major military powers are now in a state of quiet panic, scrambling to develop countermeasures to this quantum threat. The urgent scramble to hide from quantum sensors has triggered a massive new arms race in naval engineering. The most obvious countermeasure is to drastically reduce the submarine's magnetic signature. This process, known as degaussing, involves wrapping the submarine's hull in massive electrical cables and passing powerful currents through them to cancel out magnetism. Degaussing has been used since World War II to protect ships from magnetic mine. However, actively canceling the magnetic field of a modern nuclear submarine to the degree required to fool a SQUID sensor is an engineering nightmare. It requires immense amounts of electrical power and incredibly complex dynamic control systems that must adjust in absolute real time. As the submarine changes depth, heading, and latitude, its interaction with the Earth's magnetic field constantly shifts. The active degaussing system must instantaneously calculate and project a counterfield to maintain a perfectly neutral magnetic footprint. Even a momentary lapse in this active camouflage would create a spike detectable by quantum sensors above. Furthermore, the internal machinery of the submarine, the spinning turbines, the massive electrical generators, all create their own localized magnetic fields. Shielding these internal components while simultaneously canceling the external hull signature requires a level of magnetic management that pushes the absolute boundaries of current materials, science, and engineering. Because active cancellation is so difficult, naval architects are revisiting the possibility of using entirely non-magnetic materials for submarine construction. The most prominent alternative to steel is titanium. Titanium is incredibly strong, highly resistant to corrosion, and crucially, it is paramagnetic, meaning it barely interacts with external magnetic fields. The Soviet Union famously experimented with titanium submarine hulls during the Cold War. Their legendary Alpha-class submarines were incredibly fast, could dive to unprecedented depths, and possessed a significantly reduced magnetic signature. However, building a submarine out of titanium proved to be an incredibly expensive and technologically daunting undertaking task. Titanium is notoriously difficult to work with. It must be welded in specialized, oxygen-free environments, often requiring massive facilities filled with inert argon gas. The metallurgical challenges of creating a flawless titanium hull capable of withstanding the immense crushing pressures of the deep ocean make mass production economically unfeasible for most nations. Even if a nation could afford a fleet of titanium submarines, it would not completely solve the problem of quantum detection. SQUID sensors are becoming so advanced that they do not just detect the magnetic anomaly of the hull itself. They can detect the secondary magnetic effects caused by the physical displacement of the ocean water as the massive submarine moves. Seawater is highly conductive due to its dissolved salt content. As a massive object moves through the ocean, it displaces thousands of tons of this conductive fluid. This movement creates complex hydrodynamic wakes and internal waves that interact with the Earth's magnetic field, generating faint electromagnetic signatures that trail behind the submarine for miles. These wake-induced magnetic anomalies are incredibly subtle, far weaker than the signature of a steel hull. But for a highly calibrated SQUID array coupled with artificial intelligence, they are entirely detectable. You cannot move a massive object through a conductive medium without leaving a physical and electromagnetic trace. The laws of physics are inescapable. With both acoustic stealth and magnetic stealth failing, naval strategists are being forced to completely rethink the future of underwater warfare. The era of relying on a few massive, multi-billion-dollar nuclear submarines may be coming to a rapid end. The focus is shifting towards radically different operational concepts that embrace distribution and high autonomy. The future likely belongs to extra-large unmanned undersea vehicles, or XLUUVs. Instead of building one giant detectable submarine, navies will deploy swarms of smaller autonomous drones. These drones can be constructed from non-magnetic composite materials and powered by advanced fuel cells, making them incredibly quiet and practically invisible to magnetic sensors. By distributing the offensive payload across a decentralized swarm of autonomous drones, the loss of a single unit becomes tactically irrelevant. These drone swarms can coordinate their movements using localized acoustic networks, lurking silently in strategic choke points, waiting for the command to strike. The monolithic target is replaced by an elusive distributed threat. Furthermore, these drone networks can be utilized for active electronic warfare against quantum sensors. Just as aircraft use radar chaff to confuse anti-aircraft missiles, underwater drones could deploy magnetic decoys. These decoys would generate artificial magnetic anomalies, creating a chaotic environment of false positives that completely overwhelms the SQUID arrays. Imagine a battlefield where thousands of active magnetic emitters are scattered across the ocean floor, constantly pulsing and shifting their signatures. The artificial intelligence algorithms tasked with finding the real submarine would be blinded by the sheer volume of synthetic magnetic noise. The transparent ocean would be plunged back into absolute sensory chaotic darkness. The development of quantum technology is thus triggering a corresponding evolution in counter-quantum tactics. It is a modern manifestation of the eternal struggle between the spear and the shield. As SQUID sensors become more sensitive, the methods of spoofing, confusing, and overwhelming those sensors will become equally sophisticated and technologically highly complex. This new arms race will heavily rely on the integration of artificial intelligence across all domains. Machine learning models will not only be used to process SQUID data, but also to command the drone swarms, dynamically adjusting their magnetic camouflage and decoy strategies in real time. The underwater battle space will become a highly automated, algorithmic war zone. The fusion of quantum sensing with traditional platforms is also a critical area of development. SQUID data will not be used in isolation. It will be seamlessly integrated with advanced acoustic processing, satellite imagery, and intercepted communications. This multi-domain sensor grid will create a comprehensive, inescapable picture of the entire maritime environment. The timeline for this technological revolution is accelerating faster than many military planners anticipated. While widespread satellite-based quantum tracking may still be decades away, airborne and drone-mounted SQUID arrays are rapidly approaching operational readiness. The window of absolute invulnerability for the stealth nuclear submarine is steadily closing fast. We are currently standing at the precipice of a monumental transition. The acoustic era of submarine warfare, which has dominated naval strategy for nearly a century, is giving way to the quantum era. The strategic certainties of the Cold War are dissolving, replaced by a complex, highly dynamic, and technologically demanding landscape of quantum sensory supremacy. The ethical and strategic dilemmas posed by this behold are profound. Transparency is often championed as a force for peace, reducing the chance of miscalculation. But in the realm of nuclear deterrence, ambiguity and survivability are the very pillars of stability. When weapons of mass destruction are involved, absolute visibility can breed absolute paranoia. If a nation knows that its nuclear deterrent is continuously tracked and vulnerable to a preemptive strike, the pressure to adopt a use-it-or-lose-it posture increases dramatically. The threshold for nuclear conflict could be dangerously lowered. The technological triumph of quantum sensing could inadvertently create the most unstable geopolitical environment in history. This necessitates a completely new approach to international treaties and arms control. Current agreements are largely based on counting physical warheads and delivery systems. But how do you regulate a sensor technology that makes those delivery systems obsolete? The international community must grapple with the destabilizing effects of quantum sensory advancements. Despite the terrifying military implications, it is crucial to recognize that SQUID technology is fundamentally a tool of immense scientific discovery. The same extreme sensitivity that can track a submarine can also be utilized to unlock the deepest secrets of our planet. The dual-use nature of quantum physics means it holds incredible potential for civilian applications. For instance, SQUID arrays can be used for high-resolution geological surveying. They can map deep-sea mineral deposits, locate hidden geothermal energy sources, and precisely monitor the movement of tectonic plates. This could revolutionize our understanding of Earth's internal dynamics and provide critical early warning systems for devastating earthquakes and tsunamis. In the medical field, SQUID technology is already saving lives. Magnetoencephalography, or MEG, uses arrays of SQUIDs to map brain activity with unprecedented precision. By detecting the magnetic fields generated by neural currents, doctors can pinpoint the exact origin of epileptic seizures and map critical brain functions before performing complex neurological surgeries. The ability to measure magnetic fields at the quantum limit opens up entirely new frontiers in materials, science, chemistry, and fundamental physics research. We are gaining the ability to observe the microscopic interactions that govern the macroscopic world. The tools developed for warfare are simultaneously advancing the boundaries of human knowledge and capability. This profound realization highlights the interconnected nature of scientific progress. The quest to understand the bizarre behavior of subatomic particles in a freezing laboratory has directly led to technologies that dictate the destiny of global empires. The quantum realm, once a highly abstract mathematical concept, is now aggressively reshaping our physical reality. The ocean, which for millennia has been perceived as a dark, impenetrable abyss, is finally being illuminated. Not by powerful searchlights, but by the delicate, invisible interactions of quantum mechanics. The stealth submarine, the ultimate symbol of unseen power, is being unmasked by the fundamental laws of physics that govern the very fabric of the universe itself. As we navigate this new era, the challenge will not just be technological, but philosophical. We must learn to manage the immense power of quantum sensing responsibly. The transition from a world of hidden threats to a world of absolute visibility requires a profound shift in global diplomacy, military strategy, and our collective approach to international security. The integration of SQUIDs into global defense networks will require massive advancements in data processing. The sheer volume of magnetic data collected from millions of square kilometers of ocean will be staggering. Though traditional computers simply cannot handle this influx. This data challenge will likely drive the parallel development of powerful quantum computers. Quantum computers, utilizing the same principles of superposition and entanglement, could process this vast ocean of magnetic data exponentially faster than classical supercomputers. They could instantly identify the subtle anomalies of a submarine swarm amidst the chaotic background noise of the sea, creating a perfect synergy of quantum sensing and quantum computing. This convergence of quantum technologies will create an intelligence apparatus of unimaginable power. The maritime domain will become a fully integrated, mathematically predictable environment. The unpredictable variables of weather, oceanography, and human error will be systematically eliminated by the relentless precision of quantum algorithms and autonomous networks. For the sailors tasked with operating these future submarines, the psychological burden will be immense. The traditional submariner ethos is built on the confidence of remaining undetected. Operating in an environment where you must assume you are always being watched requires a completely different mindset, a transition from silent hunter to highly evasive survivor. Training doctrines are already beginning to adapt. Submarine crews are focusing heavily on electronic warfare, rapid deployment of decoys, and exploiting highly localized environmental anomalies to momentarily blind quantum sensors. The art of submarine warfare is shifting from physical concealment to complex, multi-dimensional electronic and magnetic deception strategies. We must also consider the economic impact of this transition. The cost of developing, deploying, and maintaining vast networks of quantum sensors, coupled with the immense expense of developing countermeasures and new drone fleets, will strain defense budgets worldwide. The quantum arms race will be an economic marathon, heavily favoring nations with advanced tech sectors. Smaller nations, unable to afford massive quantum surveillance networks or advanced drone swarms, may find themselves entirely marginalized in the maritime domain. The transparent ocean could widen the gap between global superpowers and regional navies, concentrating absolute maritime dominance into the hands of a few technologically elite nations with quantum capabilities. However, technology is notoriously difficult to contain. Just as nuclear technology eventually proliferated, the fundamental principles of quantum sensing will spread. Commercial off-the-shelf components, advanced manufacturing techniques, and global scientific collaboration will inevitably lower the barrier to entry for developing capable SQUID-based sensing systems. When multiple nations possess the ability to make the ocean transparent, a new equilibrium may eventually emerge. A state of mutual absolute visibility could replace mutually assured destruction. If a surprise attack is physically impossible because all assets are constantly tracked, a tense but stable peace might be maintained through the sheer impossibility of stealth. This optimistic view, however, relies on rational actors and flawless technology. In reality, the transition period will be fraught with extreme danger. The overlapping capabilities of legacy stealth submarines and emerging quantum sensors will create a highly volatile environment where misinterpretations and false alarms could trigger catastrophic global consequences. The scientific community has a crucial role to play in navigating this transition. Physicists and engineers must actively engage with policymakers and military strategists to clearly communicate the capabilities, limitations, and profound risks associated with quantum technologies. Clear-eyed scientific understanding is the only defense against geopolitical miscalculation. Looking back at the history of warfare, every ultimate weapon has eventually met its match. The heavily armored knight was defeated by the firearm. The impenetrable fortress was shattered by artillery. The invincible battleship was rendered obsolete by naval aviation. Now, the ultimate stealth platform is being dismantled by the power of superconducting quantum interference. This cycle of innovation and obsolescence is the defining characteristic of human technological progress, but the quantum revolution feels fundamentally different. We are not just building a bigger bomb or a faster engine. We are manipulating the foundational code of reality itself to achieve sensory capabilities that were previously considered strictly in the realm of fiction. As we stand on the threshold of this new era, the ocean remains as vast and powerful as ever, but our relationship with it has permanently changed. It is no longer a dark abyss that can hide our most destructive creations. It is a dynamic, interconnected environment that can be read and interpreted with mathematical precision by the unblinking eyes of quantum sensors. The story of the SQUID magnetometer is a testament to human ingenuity. It demonstrates our relentless drive to understand the universe and weaponize that understanding for strategic advantage. It shows how the most abstract theories developed by physicists scribbling on chalkboards can eventually reshape the balance of power on a global, civilization-altering scale. The stealth nuclear submarine, a marvel of 20th century engineering, will eventually join the ranks of historical military artifacts. It will be remembered as the apex predator of a bygone era, the undisputed master of the acoustic ocean, ultimately dethroned not by a louder sonar, but by the silent, inescapable logic of quantum mechanics and magnetic field detection. The future of naval warfare will be defined by swarms of autonomous drones, vast networks of quantum sensors, and artificial intelligence battling in the electromagnetic spectrum. It will be a faster, more complex, and infinitely more visible battlefield. The era of hiding in the deep is officially over. The era of surviving in the transparent ocean has just begun. As we continue to unlock the secrets of the quantum realm, we must remain acutely aware of the profound responsibilities that come with such immense power. The technologies we create have the potential to ensure global stability or trigger unprecedented conflict. The choices we make in the coming decades will determine the ultimate legacy of the second quantum revolution. The invisible world beneath the waves is finally coming to light. The intersection of quantum physics, advanced engineering, and geopolitical strategy has created a fascinating and terrifying new frontier. We will continue to monitor these incredible advancements and bring you the science behind the headlines. The universe is complex, but understanding it is our core mission. I am Dr. Sachi Vale. Thank you for joining me on this deep dive into the quantum threat to stealth submarines. If you found this exploration of modern science and geopolitics fascinating, please support our channel. Until next time, keep questioning the world around you and never stop exploring the incredible phenomena of our universe. This is Science Aura, signing off.